Your motor is losing steps, not because of wiring, not because of current, because of how you're accelerating. Look at this velocity profile. At the start of acceleration, speed jumps instantly, same at the end. Those 2 points are where your motor gets hit every single move. Here is exactly why and how to fix it. This is the trapezoidal profile, 3 phases: accelerate, cruise, decelerate. It's the default in almost every motion controller, simple to compute, easy to implement. But look at the transitions. The acceleration changes instantly, 0 to maximum in 0 time. That is not smooth. That is a mechanical hit. That instantaneous change has a name: jerk. The rate of change of acceleration, da over dt. In a trapezoidal profile, jerk is infinite. The acceleration slams to maximum. In an S-curve profile, jerk is finite. The acceleration builds gradually, holds, then fades. Infinite jerk means a force impulse. That impulse travels into the rotor. The rotor overshoots its target. It oscillates before settling at the wrong speed that matches the motor's natural resonance. Vibration multiplies 5 to 10 times. Missed steps. The S-curve profile fixes this with 7 phases. Phase 1 through 3, acceleration builds gradually. Phase 4, constant velocity. Phases 5 through 7, deceleration ramps down. No sharp corners, no instant transitions. The rotor is never hit. It is guided. Here is where it gets interesting. To complete the same move in the same time, the S-curve needs higher peak acceleration than trapezoidal. Trapezoidal, 500 millimeters per second squared. S-curve, 785, 57% higher peak. But the load sees far less shock, and settling time is 25% shorter. The math: peak S-curve acceleration equals pi over 2 times the trapezoidal value. Pi over 2 is 1.57. That is where the 57% comes from. The jerk is finite and controlled, predictable at every point in the move. Same motor, same distance, same move time. S-curve settles at 75% of trapezoidal time. That difference is real throughput. In CNC milling, axis reversals with trapezoidal generate chatter marks. With S-curve, the reversal is smooth, clean surface, longer tool life. In 3D printing, ringing and ghosting come from sharp acceleration changes. S-curve reduces the excitation energy. Corners become smoother. Ringing drops 40 to 60%. In pick and place, settling time is the bottleneck. With S-curve, settling is 25% faster. Placement error drops from 0.3 to 0.05 millimeters. Stepper speed equals step pulse frequency. Trapezoidal means constant delay between steps. S-curve means the delay changes every step using a cosine function. Slow at the start, fast in the middle, slow at the end. In Arduino, one line of math with cosine gives you the full S-curve delay. In Python, generate the delay array with NumPy before you move. Accelerate, run, decelerate. When to use which: simple positioning, trapezoidal. CNC, pick and place. 3D printing, S-curve. Heavy load near resonance, S-curve. Motor losing steps at acceleration, try S-curve first. Infinite jerk, mechanical shock. Missed steps, S-curve fixes the root cause. 7-phase profile, finite jerk, controlled acceleration, same motor, different pulse timing, completely different behavior. Next, stepper motor versus servo motor, when to switch and what you actually gain. If the physics made sense, subscribe, more coming.